What if language models could learn, forget, dream, and remember more like we do? In today's episode, we explore three striking new papers on continual learning, synthetic data generation, and the hidden role of time in pre-training. From Google-affiliated researchers Sleep-inspired LLMs to Alibaba and Huzhou Normal University's StreamSynth and Kyutai's work on chronological training, these ideas could reshape how systems like Llama and Quinn grow smarter over time. Let's explore the first paper. Language models need sleep learning to self-modify and consolidate memories. Language models need sleep learning to self-modify and consolidate memories proposes a biologically inspired life cycle for LLMs built around Google-affiliated authors Ali Beiruz and Vahab Mirakni that replaces the usual train, test split with alternating wake and sleep phases. In the wake phase, a continuum memory system updates modules at different frequencies. In sleep, the model expands capacity by activating new low-rank experts and performs knowledge seeding and upward self-distillation from a faster, smaller memory block into a larger, slower one using generalized knowledge distillation plus imitation learning with semantic and Levenstein rewards. A second sleep stage, dreaming, generates synthetic curriculum data and fine-tunes with ReStem style selection and LoRa to recursively improve the model without external labels. Across Llama, 3B, 8B, and Quinn 3 backbones, the method improves class incremental learning on Clink, Banking 7.7, and DBpedia, strengthens long context retrieval on MKNaya, Long Health, and Quasper, and reaches nearly perfect performance on Babylon, up to 10 M tokens. On factual incorporation from Squad, it outperforms Seal, and on FewShot Arc, it reaches an 80% success rate versus 72.5% for Seal. The key novelty is not just self-distillation, but periodic consolidation into newly expanded parameters, followed by controlled synthetic dreaming, which the authors argue reduces catastrophic forgetting while preserving and abstracting newly acquired knowledge. Let's explore the second paper. Make LLM learn to synthesize from streaming experiences through feedback. This paper from Huzhou Normal University and Alibaba Group introduces StreamSynth, a new setting for synthetic data generation in which tasks arrive sequentially, and a model is trained to learn transferable synthesis behavior from past experience, rather than generating each dataset in isolation. The authors propose SynLearner, which combines diversity-aware initialization with hierarchical reward optimization. Prompts are dynamically instantiated and evolved to expand both depth and breadth of synthesis patterns. Then the model is fine-tuned and reinforced using a dual reward that mixes sample-level quality, structural validity, fluency, and task relevance with set-level distinctiveness computed from batch embedding density. Experiments on the Yelp, Amazon, Yahoo, and MNLI stream with LLAMA3, 18B, and Quinn 2. 57B show that SynLearner consistently outperforms direct prompt-only synthesis and continual learning baselines such as GORP, FAPM, NCL, and Seeker, with especially strong gains on later tasks. For example, on Llama 3. 18B, it reaches 82.5 accuracy on MNLI versus 80.91 for GORP, and on Quinn 2, 57B, it improves MNLI to 86.56 versus 85.53. Ablations confirm that removing dynamic prompting or GRPO-based reward optimization degrades performance, and TSNE plus cross-task heatmaps show broader coverage and better forward transfer. The method also generalizes to reasoning, improving GSM 8K and Math 500 by 2.81 and 7.8 points on Llama 3 18B, with larger gains on Quinn 2 57B. Let's explore the third paper, Understanding Data Temporality Impact on Large Language Models Pre-Training. Understanding Data Temporality Impact on Large Language Models Pre-Training by Romain Fabre, Hippolyte Pilchen, Franck Siniatala, Patrick Perez, and Edouard Grave at Kyutai argues that standard shuffled pre-training obscures when facts were learned and produces a measurable knowledge horizon lag. The authors pre-trained matched 6 B parameter transformer decoders on 2, 5 T common crawl tokens in 2 regimes, a globally shuffled baseline, and a strictly chronological curriculum, spanning 2018 and 2025 using Atom W, a 4096 token context, and 128 H100 GPUs. To evaluate temporal grounding, they introduced Kairos QA, a 7,167-pair benchmark built from Wikidata subject relation year triplets, filtered for temporal variation, popularity, and ambiguity, then tested in both close and generative settings. They also compare against TACA. On OLUMs, sequential training matches shuffled training on general language understanding, reaching comparable final scores while changing the learning trajectory. On Kairos QA, however, chronological ordering consistently yields fresher factual knowledge. Sequential checkpoints peak in the year immediately before their cutoff and outperform shuffled models on recent facts, reversing the recency decay seen in open source baselines such as Llama 3.18b, Gemma 3, Qwen 3, and Omo 3. The effect is strongest on 2023-2024 questions, where shuffled models often approach random accuracy, while the sequential model retains a clear margin. The paper also shows that simple replay or model soup only partially mitigates catastrophic forgetting, indicating that temporal ordering improves factual freshness but does not fully solve historical retention. That's a wrap on today's AI paper highlights. Thanks for watching.